Hi, I'm Bill Reinhardt from the University of Manchester, and this is our series of tutorials using live Matlab scripts for inverse problems in tomography. And today we're just going to do a little Tikhonov regularization of a 2D tomography problem. Let me share screen. Okay, so this live script Matlab code can be found in the link that I'll put at the end. Tikhonov and generalized Tikhonov. So we're going to make a matrix for the Radon transform in 2D. We're going to use Air Tools 2 for that. The links there. Download that. Make sure you can get it to work. Set up, puts the paths on, and so on. It's just a simple library to make matrices of tomography problems so that you can test different regularization and iterative algorithms. And it's described here in the reference that I'll show you at the end. It's in this script. Okay, so first of all, in this kind of live script notebook, the grade sections are the executable code. And I can just do run section there. And it shows us the test image. Okay, about that. Just wondering whether I set up the path. You have to make sure that Air Tools is in the path. Okay, so by the way, the command window's here, and it's kind of you have all the variables that you make in the command window if you want to play, but you can also edit the commands in this box. I'll start a new section, edit that. Anyway, so we've got a test problem. Parallel tomo makes an A, an X, and a B. A is the system matrix, B is the right-hand side, the sinogram data, as we call it in the tomography problem. And X is our test image, which is, I don't know, something a bit like a head. Now, AX should equal B. So we could try and solve it using the Matlab / operator that does a least squares solution. A's come out as a sparse matrix, as you see over hovering it. Let's just run that section. And so we're maybe not expecting it to work because the / operator just does the least squares with no extra regularization. Of course, it is an inverse problem, so it's ill-posed. The Radon transform is mildly ill-posed. So in the end, it's not too bad. So looks pretty good, in fact. So to see what's going on and why that might work, we can do the SVD, the singular values. I've done full of A because A is a sparse matrix and SVD expects a full matrix. And then I plotted on a log-log scale the singular values. And you can see until they fall off dramatically because of the smallest dimension of the matrix, which I've set, by the way, to 50 by 50 there. So N is 50. On a log-log scale, it's going more or less straight, which means that it's a power law. And so, of course, that's consistent with what we know from the theory. It also means it's mildly ill-posed, something a little bit like taking a numerical derivative or something like that, a power of a differential operator. Okay, what happens if we add some noise? So here's a quick hack to mess up the data with some noise. So rand n makes normally distributed mean zero variance one pseudo-random number, so a sample from that distribution. To scale it properly, I've multiplied by the norm of b, so it's scale invariant, and I've made this 0.1%. So the standard deviation is 0.1% of the norm. So now if we plot it with and without the error, this is the sinogram of that sort of head-like phantom. And you can see the sine waves from the structures in that object. And then here, I'm not sure if it will come across on this screen, but when you run it yourself, you'll see there's, you can definitely see the noise in the bit outside the object where there shouldn't be any attenuation of the X-rays. And if you compare the pattern, you can see that it's a bit speckly. So there is some noise, it's pretty recognizable. It shouldn't be so hard to compensate for that, given that it's only mildly opposed. Okay, now if we try backslash, well, it doesn't work so well because there's no regularization to control the effect of the errors, even though the errors are very small. And so this would be the same if we used an iterative solution, iterative solver that converged to the least square solution. This is what it would converge to. If you use one that converges very slowly and stop early, you obviously get something a bit different. But this is the thing that actually best fits that noisy data. And you can see the outline, but a little bit of structure and mainly rubbish. So that's with no regularization. I think I have a cross-section through it sometimes, but not always, plotting a cross-section of the image, in this case, across the middle, gives you a little bit more insight because your eyes fool you on images, but well, I'm not sure. You can see this big spike, which is kind of wrong in the middle. Okay, so now we do a little bit of Tikhonov regularization, which is pretty much the first thing that people try with an ill-posed inverse problem. It's so simple, it's regularly reinvented and called by different names. For example, ridge regression is another name for it. I've taken the norm of the matrix, the operator 2 norm, really just to scale things. So I've set my Tikhonov factor to 0.5 times the 2 norm. I mean, just so it's invariant under scaling the A, and we can compare Tikhonov factors. I then form an augmented matrix, which is the matrix A that I already have, and the semicolon means I then stack another matrix underneath, which has to be obviously the same width, so the same number of columns. And I put the identity matrix n squared by n squared, right? So n is 50. And so that's the same number as the number of unknowns, the pixels, and so it has the right number of columns. So I've stacked this underneath A, and as you can check for yourself, this means that the if I do the least square solution on this system, so A is for augmented, the B with the noise augmented, I just put zeros of the right size for it to work. And then the Tikhonov solution, I just do A augmented backslash B augmented. And then Matlab just automatically does a Tikhonov regularized solution. And you see, well, you can play with the choice of regularization parameters. It's very easy to make a slider if you want to recalculate it. Oh, I've got the shape displayed differently. You probably have to change the axes. I'm not sure it's meant to be round. Anyway, you see the distinctly see the edge and these two blobs and this blob, and then some noise here. So, of course, you can play with the Tikhonov factor, and there's some sensible ways also to calculate that. The cross section looks much more sensible. It has the structures that we saw in the original image. Another thing we can do instead of using the identity matrix is use a matrix that does differences between neighboring pixels. In other words, a discrete gradient operator. I just cooked this up by hand in Matlab. If you make a matrix whose diagonals are minus ones and ones, right, on the diagonal, and they one off the diagonal, and to put boundary conditions on it as a gradient, we just put the last one is 0, actually. So I divided by n because that seemed fair. This is a one-dimensional derivative. Now, to make a two-dimensional derivative, first of all, we differentiate along the rows of the image and then the columns of the image. To make a matrix that does that, we use the Kronecker product with the identity both ways round, and then stack that into a matrix. And the output of that is a discrete gradient with the gradient in the two different directions in the different blocks. I probably didn't make that sparse, so that makes it sparse. And if you do spy of it just to check that it looks right, if you zoom in, you can see that this is exactly what you expect. These are the non-zeros in this matrix because they're 1 and -1. Now, if we use generalized Tikhonov with this matrix L, then it penalizes the discrete gradients, the norm squared of the gradient. So it tends to typically smooth the image off a bit. You have to think a little bit about what would be a fair Tikhonov factor. And so I just use the same one, but well, it's got a slightly different image. Well, you can decide if that's better or worse, but you can certainly play with that. So for suggestions for thinking, I've said have a look at the regularization factor and see if that's actually a fair comparison, because I didn't look at the norm of L to compare it. And was I just lucky with the choice of regularization parameter I used? Try some difference. Is it robust with respect to that choice, or is it really picky? And what happens when you change the level of noise? Obviously, you need a little bit more regularization, but how much? And also, while I've displayed the image is, I always tell people that actually how well it fits is just as important. So, in other words, if you do AX minus B, how well your X fits, and plot that as an image, reshape it and plot it, then that will be a sinogram, and it will tell how well you're fitting the data. Because Tikhonov regularization is a compromise between fitting the data and not having too silly an image. So silly in this context means that the regularization term shouldn't be too big. So it penalizes that. And so you can have huge values for standard Tikhonov regularization, or if you use the gradient version, then nearby pixels are really softly constrained to be quite similar. Okay, we've got some references. I recommend you have a look at our book, which is focused on tomography problems and sort of just the minimum that you need to be able to do X-ray or similar tomography problems, mainly in 2D. Air tools too is documented in this paper. So I recommend if you use it, you reference this paper, but it's if you just download it, it's fairly self-explanatory how to use in the helps for the functions. Okay, so next up, we're going to look a little bit more at the singular value decomposition. We looked at singular values, at least, of this 2D Radon transform.